Well, okay, we'll start. So, like I said before we got set here, so we're going to talk about modulation and some things about modulation. And let me share my screen. And the first type of modulation we're going to talk about is amplitude modulation. So this is really the simplest form of modulation. So if you can think of, and we'll think of this as just as a voice or a music signal, any kind of audio signal. And this top one here, okay? This is just a simple sine wave, but it could be any kind of audio signal. When we mix the two, mix the audio signal with a carrier signal, and this is the signal at a frequency, at a radio frequency, you get this kind of combination of the two. And what's called the modulation envelope is sort of this outline here, okay? And that's the same as the audio signal, right? So, question, what type of modulation varies the instantaneous power level of the RF signal? Answer, amplitude modulation. You know, because it's varying the voltage, it's also varying the power. Question, what is the modulation envelope of an AM signal? Answer, the waveform created by connecting the peak values of the modulated signal. So the red here is actually the signal you're receiving, but the modulation envelope is what you're going to detect. When you pass this signal through the detector in a superheterodyne radio, you get the audio that you modulated the signal with in the first place, or you're supposed to. Let's put it that way. And so let me just see if I can find the. So here's the superheterodyne receiver again. So you know that AM signal would come in here. It actually would get mixed and turned into an intermediate frequency, right? But this demodulator restores basically, you know, grabs detects the modulation envelope of the signal, and that's usually an audio signal, and it just sends it out the speaker. And it's an AC signal all the way through. There's no DC about it, right?
So it's the very last stage where it gets demodulated.
Right. Well, close to the last stage. You always have some audio amplification, but it's close to the last stage. You know, and in a CW or sideband, this demodulator is called the product detector. In a simple AM radio, it's just it can be almost as simple as a diode detector.
So depending on what kind of mode or what kind of that demodulation is going to be amplitude that you're taking off of there, or if it's going to be a frequency shift. Is that right?
Well, it's not a frequency shift. You're detecting. Let's go back to the this. What you're detecting is this, what's called the modulation envelope. You're basically getting rid of all this RF, and then what you're left with is the modulation envelope. And that's since that's what since that signal is a good facsimile of what you modulated the transmission with in the first place. You know, if it was voice, then you'll hear a voice on the speaker of the receiver. That makes sense?
Yeah, I got it.
Okay. So let's talk about bandwidth now, right? And I was going to, I'll just have to draw this, but oh, hang on. Let me do this. So this is frequency. Here's the carrier frequency. And remember I said that when you amplitude modulate a signal, you get two sidebands. And if you limit the audio that you modulate the signal with to like 3 kilohertz, which is what you need to do in amateur radio, the bandwidth will be 3 kilohertz. It's actually 3 kilohertz on both sides, right? Because these two sidebands are redundant. So the bandwidth of a single sideband signal will be 3 kilohertz. An AM signal has both sidebands, so AM will be 6 kilohertz. Now, FM signals, if you remember from your tech days, the tech questions, is like 10 kilohertz. Ten to 15 kilohertz. So the question here is, which of the following phone emissions uses the narrowest bandwidth? Answer, single sideband. And the other choices are double sideband. And, you know, double sideband is the same as AM. That's 6 kilohertz. FM, which is 10 to 15 kilohertz. And they say phase modulation, PM, and that's the same because that phase modulation is sort of just another way to generate an FM signal. All right, so any questions about that? And you know, why is this important? Well, you know, in HF, the only band you can use FM on in the HF bands is 10 meters. And why is that? Because 10 meters, we have a bandwidth of 1.7 megahertz. So we can fit some FM signals in there. And normally it's above 29 megahertz where you'll find FM. All the single sideband and CW happens below 29 megahertz. But on say the 40 meter band, for example, you know, we have only 300 kilohertz. And even then, for phone, we have only, let's see, what do we have? 175 kilohertz for phone signals, according to the band plan from the FCC, the frequency allocations. So, we could fit maybe only, 10 to 15 FM signals in the whole band. Well, that's no good. So that's why we use a single sideband, because you can fit many more signals into the band. There's no technical reason not to use FM on 40 meters. The only reason is we have a limited bandwidth. Okay, let's go back to this diagram now. So, as you can see, this modulating signal causes the amplitude to go up and down. If you had, oh heck, see if I can draw this better. If you were able to modulate this signal such that the minimum, well, that's not so good, such that the minimum here, this minimum amplitude was 0, we'd say this is 100% modulation. And that's the ideal point. If you can get, and how do you do that? You adjust the microphone gain such that this amplitude reaches 0 at this point, right? So in this case, this is probably about 90% modulation, which isn't bad, but at 100% modulation, you're getting the most power out because your voice is actually sort of producing the power, if you will. And that's why like if you set up you say you set up an HF station and you tune around and you hear something, even if you hit the push to talk button on your radio, unless you speak into that radio, you're not transmitting anything because there's no audio input, so you're not getting any modulation. And the way balanced modulators work, remember, is that they only output the 2 sidebands. If you have no input, you have no sidebands. So at this point is 100% modulation. Now, if you set the mic up more than that, what happens here is you get this kind of thing happening. And this is bad. This is greater than 100% modulation. And actually, you don't actually get this here. You get something that looks like this. And this, what the end result is a distorted signal. Because there's times here where you're not transmitting at all, and then you're overdriving on the other part. So, question, what is the term flat topping when referring to a single sideband phone transmission? Answer, signal distortion caused by excessive drive. Question, which of the following is an effect of overmodulation? Answer, excessive bandwidth. I mean, you'll actually generate spurious signals when you overdrive your signal, and that's why guys will tell you on the air, if they hear that, they'll say, "Yeah, crank your mic gain down. You're overdriving the radio." Like I said, that's the sweet spot, 100% modulation. And if it's less, say it's only 50% modulation, well, you're not getting all the output power that you might get. All right. Think about that. And if there's any questions, we'll tackle them later. Now let's talk a little bit about frequency modulation. So here we have the same audio signal, right? Here's the carrier signal. Although this is, unlike the other one, this is probably at VHF, not HF. And here we have the modulated signal. So you'll see when this goes negative, we get a lower frequency. When it goes positive, we get a higher frequency. And the bandwidth is, approximately 10 to 15 kilohertz. So question, what is the name of the process that changes the instantaneous frequency of an RF wave to convey information? Answer, frequency modulation. Now, and this is something new to me. I really had no experience or idea how they actually generated FM signals. I mean, aside from these block diagrams. And apparently, most of these radios are using a process called phase modulation. And this is a block diagram of a phase modulated transmitter. What they do in phase modulation is actually change the phase of the oscillator of the carrier here in proportion to the audio input. So the louder the audio input, the greater the phase change, which translates into a frequency change. And they call it a reactance modulator. Well, why is that? Well, if you remember the oscillator, it used an LC circuit. No, that's not very good. An LC circuit to generate the frequency uses the resonant frequency here. Well, if you change the L or the C, but usually the C, then you're going to change the frequency. And that's what they do. In fact, some of these things use what's called a varactor diode. A varactor diode is a diode, but it's used for its capacitive characteristics. And by changing the voltage across a varactor, you change its capacitance. So if you use a varactor here instead of the capacitor or across the capacitor, you're going to change the reactance of that capacitance, which changes the frequency of the oscillator. So question, what is the name of the process that changes the phase angle of an RF signal to convey information? Answer, phase modulation. Question, what emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? Answer, phase modulation. So the reactance modulator will produce phase modulation. And I was looking up these things on the internet, and you can do the same. If you want to know exactly how these circuits work, you can find phase modulator circuits on the internet. Like I say, I've never tried this myself, so I don't know that I can speak too much more about that. But this is pretty cool, actually. Pretty interesting way to do it. And you see here, there's a frequency multiplier. We talked about that. And in fact, I think there's still some questions coming up later on this. Normally, this is kind of like a 12 times multiplier. So to get up to 2 meters, say, you're generating like a 12 megahertz signal here. So that when you go through the frequency multiplier, you get a 144 megahertz signal out here. All right, any questions about that? Okay, so let's talk about frequency shift keying. This is another type of modulation, right? But mostly we use this for data. And this in the simplest case here, this could be like an RTTY transmission, radio teletype. Radio teletype, we're shifting between two frequencies 170 hertz apart. So this frequency would be 170 hertz less than this frequency. And the modulating signal, if you will, is a digital signal, 1 or a 0. Now, you can do this with most transceivers now, but they also do this with audio too. Like you can, that's called audio frequency shift keying, right? Because remember, if you remember the sideband thing, right? If you put a 1,000 hertz audio, and usually it's like 2225 and 2395 or 2225 and 2050 or something like that. But anyway, if you put those signals in, you generate a sideband here for the 0 and then another sideband here for the 1, and you just switch between those two. So you can do this with audio, and because it's single sideband, right? You're not getting the carrier. So this works with audio too, although it doesn't work as well as if you can actually change the frequency of the carrier frequency. That works a little bit better. If you can feed a digital signal in and then get the program the radio such that it'll change VFO frequencies, that's a little bit better. But anyway, it's called frequency shift keying, or FSK. Question: how is an FSK signal generated? Answer: by changing an oscillator's frequency directly with a digital control signal. And that's sort of real frequency shift keying. This is audio frequency shift keying. So let's talk about phase shift keying now. Another way to send digital information over amateur radio is what's called phase shift keying. And in phase shift keying, what you're doing is you're changing the phase, not the frequency. So and it changes when the digital signal changes. So you get a phase shift here, you get a phase shift here, you get a phase shift here. And that corresponds to the digital signal changing. So if you listen to something like PSK31, if you listen to a PSK31 signal, you hear a single tone, but you hear it waver because every once in a while it changes phase. And this works great, especially with audio frequency shift, or with an audio signal, right? Because you're not changing the frequency necessarily, but you're just changing the phase, and that's easy to do it with an audio signal, especially if you're digitally creating that audio signal, right? And that's what a PSK software program does. It generates this waveform digitally, and then sends it through the audio card of the computer.
Dan, question.
Yeah.
So when you say phase, are you talking about through the 360-degree circle of a waveform?
Right, right. And I mean, you see right here, right? Instead of being a nice sine wave, here it just changes direction, if you will. That's actually a phase change. And in this case, this is called BPSK, right? Binary phase shift keying. Because you only got two changes, right? And it corresponds to the 1 or the 0. This is the kind of keying that PSK31 uses.
So it's out of phase exactly in the other direction. So 180 degrees.
180 degrees, right? That's what I was just going to write down. 180 degrees phase change. Whoops. Degrees phase change. Now, let's compare this to the next type of phase changing, what's called quadrature phase shift keying. And in this mode, you can change phase any one of these 4 types, or by any one of these 4 degrees, if you will. And because you have 4 now, every time you have a phase change, you get 2 bits instead of just 1 bit. So a phase change of 45 degrees corresponds to a digital value of 0, 0. 135 degree phase change corresponds to a 0, 1. 225, 1, 0. 315, 1, 1. The quad comes from, you have 4 different phase changes, or amount of phase change, if you will. It allows you to send twice the information in about the same bandwidth. And that's the question here. Which of the following is characteristic of QPSK 31? Answer, all of these choices are correct. It is sideband sensitive. So if you were going to use this mode, you want to make sure and most of these are on the upper sideband, no matter what band you're on, right? So you want to make sure you're transmitting upper sideband. Answer, its encoding provides error correction. Its bandwidth is approximately the same as BPSK31. So with a little extra bandwidth, you get double the data rate. Any questions about that? The sort of the premier programmer, if you will, for digital modes is FL-Digi. People complain about it a lot because it looks like the user interface looks like it came right out of the 1990s. And it did, because that's when I think the guy probably started writing this program. And the guy who's responsible for it, he doesn't put a lot of effort into the user interface, or at least the way it looks. But he supports like almost every kind of digital mode you can think of outside of the WSJT modes. The WSJT modes are things like FT8, JT65. I think there's MSK144. All these really weak signal modes here. But FL-Digi will do teletype, PSK31, It even has some CW decoding in it now. So almost all these other digital modes, if you, let's put it this way, if you had these two programs, you would be able to send and receive almost all the digital modes available. And I mean, it works great. And you could download this it's a free program. Both these programs are freely downloadable, and just look at all the different digital modes available. And some of them use just regular phase shift keying. Some use quadrature phase shift keying. So some use like little variants on each of these because some guy thought it would be cool to try it. Seriously. And they all have their advantages and disadvantages. One of them, I've worked some PSK 31, I've done some FT8, and there's another one I haven't tried called Olivia, just like the woman's name, and that's supposed to be really good in poor band conditions. I'm not exactly sure why, but that's good. There's another one called Throb, and it's called Throb because that's what it sounds like. What I do, if you have an HF radio, just listen on 40 meters, like from say 7070 up to 7100. That's where a lot of these digital stations are located. And this throb, I mean, you'll be able to tell it right away because that's what it sounds like. So there's a lot of amusing sounds you'll be able to hear. And then there's I should have the information here, but I don't. There's actually an Android app you can download. Again, it's free, that you can hold it up to the speaker of your radio, and it'll attempt to tell you what kind of digital signal it is, and it's using some kind of digital signal processing to process the sound and figure out from the characteristics what kind of digital modulation it really is. So that's kind of an amusing thing. Any questions about this? All right. We'll talk. Speaking of FT8, I'll talk a little bit about FT8 now. I don't have a slide for this, but FT8, the 8 in FT8 stands for 8 tones. So it sends one of 8 tones, and that's the question here. What type of modulation is used by the FT8 digital mode? Answer: 8-tone frequency shift keying. So, if you go back to that, I can do that actually. So here's the frequency shift keying. It's just shifting between 2 frequencies. This will actually shift between 8 different frequencies. And that's part of the way it is so good in conveying information. The other thing is it's pretty slow. So, the receiver has to figure out these tones, and with 8 tones, you get 3 bits, right? Because if you had 8 tones, you get 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So, oops, I'm missing one. Where am I? 3, 4, 5, 6.
001.
Oh yeah, 001. So each of these tones stands for one of these values. And so that's sort of how it, it's slow, but it still conveys the information. In FT8, you have 30-second transmissions, and I forget how many characters you send, but it's not that many. So each character may take, a fair amount of a second. And then too, the way it works is that both the receiving station and the transmitting station have to be time synchronized. So to operate FT8, you have to download or get your computer to always keep the clock up to date. So that's another way that this is another trick of the FT8 trade, is that this transmitter and receiver are time synchronized. And I think you have to be within, like, I'm tempted to say a tenth of a second, but it might actually be tenth of a millisecond. I don't know. It'd probably be more like tenth of a second. But anyway, that's how they do it. And so it's listening for tones at certain times, and then when it hears the tones, it then generates the 8 different digital combinations, and then changes the data stream into whatever the characters are. And that time synchronization gives a very good very good signal to noise ratio performance. So, there are signals, FT8 signals, you won't be able to hear with your ear that the computer, because it's a computer, can pull out of the mud. And that's the next question. Which of the following narrowband digital modes can receive signals with very low signal to noise ratio? Answer FT8. Some people really love FT8. Like there's a guy in our club who he just got into ham radio a couple of years ago, and he's mostly an FT8 user. He does, when he gets on HF, he uses FT8, and in the 2 or 3 years he's been a ham. He's worked like 150 countries. I mean, he's got more countries than me, and it's because he's using this FT8. Any questions about that? FT8, 8-tone frequency shift keying. Remember the 8s. It sounds kind of eerie too when you hear it. I should have had an audio. I'll have to remember to do that next time. Let me make a note here. Because you could actually hear the 8 tones. I mean, you'd have to really be good to pick them out. But I mean, you can hear the tones shifting. So now let's get back to the superheterodyne receiver. And I realized as I was going through this that I probably could organize this a little bit better, and I'm sorry about that. I might try and work on this the next class. So you're kind of the guinea pigs here, but or maybe reorganize it a little bit as far as the study guide itself goes. But anyway, we'll talk a little bit about this. This is again how we decode the signal or demodulate the signal. So, question: what is another term for mixing of two signals? And this is called a superheterodyne receiver, right? And why is that? Because we use a process called heterodyning. Superheterodyne receiver. Whoops, come on. Oh, come on, what's going on here? Heterodyne receiver. And the process of mixing the two signals is called heterodyning. So that's why it's called a superheterodyne, because we're mixing two signals. That process is called heterodyning. What combination of a mixer's local oscillator, that's the local oscillator, and RF input frequencies is found in the output. Answer the sum and difference. So what you get here is that both the sum and the difference of these two frequencies. So if you wanted to receive a signal at 14.2 megahertz, and your intermediate frequency was 455 kilohertz, you might want to set your local oscillator to 14.655 megahertz. That will give you two frequencies here, 455 kilohertz and the sum too. So 28 or 28.855. Well, when you run the that signal through this filter, you get rid of this and you get 455 kilohertz. So the mixer produces the sum and the difference. Question: which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? Answer: the local oscillator. Now, one problem with this approach is that there's another frequency that'll produce a 455 kilohertz output, right? That's 14.655 plus 455, or let's see, what is that? 15.100, 110, I guess. So, back in the old days, if you had a really cheap radio, which I did, you would sometimes hear, and this frequency is in the 19-meter broadcast band, shortwave broadcast band. Sometimes you'd hear like Radio Moscow when you're trying to listen to a sideband signal on 14.200 megahertz. This is called the image response. So question: if a receiver mixes a 13.8 megahertz VFO with a 14.2, I should have used these frequencies in my example here, mixes a 13.8 megahertz VFO with a 14.255 megahertz receive signal to produce a 455 kilohertz intermediate frequency, IF signal, what type of interference will a 13.345 megahertz signal produce in the receiver? Answer: image response. And the reason for that is there's two frequencies that will produce a 455 kilohertz output from one local oscillator frequency. And this is all if all these circuits work in a nice linear fashion. Sometimes they don't, however. And that's where you get a thing called intermodulation. That happens when these circuits don't operate linearly. And you can, what intermodulation produces is something called spurious signals, which, as the name might imply, are not very predictable. They could be any crazy frequencies. Sometimes, especially in the older radios, you'd hear something called a birdie, because that was one of these spurious signals. Often, you'd be tuning along, you hear this beep, and then that's just a spurious signal being generated by the receiver itself. So question, what process combines two signals in a nonlinear circuit or connection to produce unwanted spurious outputs? Answer, intermodulation. Any questions about that? Trying to figure out when I should take a break here. I'll go through one more little section here. So let's go back to this FM.
I was wondering why specifically 15.110 megahertz.
Say again?
Why specifically 15.110 megahertz?
Oh, because so you get the sum and the difference, right? So if the input was 15.110 and your local oscillator was 14.655, 15.110 minus 14.655 gives you 455 kilohertz. So both of these frequencies will give you 455 kilohertz at the output of this mixer.
Okay, thank you.
Yeah. You know, and having said all this, most modern radios don't do this anymore. I mean, you know, that's why asking these questions is almost like I almost have to apologize for them, because you know, if you go out and buy like an IC 7300, for example, it's going to use it's all software defined radio now. So you know, there may still be a mixer in there somewhere. Sometimes they'll you know, up convert and down convert a little bit, but for the most part you don't have these problems because we're not using this analog method anymore. You know, a software defined radio, the signal comes in from the antenna and it goes right into an analog to digital converter. And it just converts it into a stream of ones and zeros. And, you know, that goes into digital signal processor. And, you know, and then the digital signal processor spits out audio. You know, it's like, that's it, you know. So it's almost crazy to like be talking about this. Although, I don't know, I suppose in a way it's good to understand it, but we you know, most modern radios don't do this anymore. Oh, let me find the FM transmitter again. So this is the FM transmitter again. And like I say, you know, we have this multiplier here that multiplies the signal, you know, so allows you to use an oscillator section that can oscillate at, say, 12 megahertz instead of 144 megahertz. And that, you know, that's much easier to do at 12 megahertz than at 144 megahertz. Then use a frequency multiplier to get you up to 144 megahertz, assuming this you want a 2 meter output. So question, what is the stage in an VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? Answer, the multiplier. Question, what is the frequency deviation of a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz 146.52 FM phone transmitter. So 12.21 times 12 gives you 146.52. That's where they got the number 12.21. And so we're generating a deviation in this signal, right? Because by the time you get out here, you've got an FM signal at 12 megahertz. So the question is, how do you get to a 10 to 15 kilohertz deviation out here? What would be the deviation back here? And they're actually asking for a 5 kilohertz deviation. So what change in frequency here will give you 5 kilohertz here? Well, it's 5 kilohertz divided by 12, or 416.7 hertz. So that's what the deviation has to be in the exciter section. Question, what is the total bandwidth of an FM phone transmitter having 5 kilohertz deviation and 3 kilohertz modulating frequency? Answer, 16 kilohertz. And the way you have to use this formula, which again, you won't be able to look in a book like I did to write this section in the study guide. So it's almost better just to, I hate to say it, but memorize the answer. But this is how you do it. Bandwidth equals, make sure I get this right, 2 times the deviation, or delta F, plus FM, which is the modulating frequency. So delta F, 2 times 5 kilohertz, plus 3 kilohertz, which is the modulating frequency, or 16 kilohertz. That's the bandwidth. Yeah, I had when I first wrote this, I had no idea how the calculation should go. So I had to look this up in a book. And like I say, unfortunately, you won't have that, but this is the equation here. And the answer, remember, is 16 kilohertz. All right, let's take a break till the top of the hour. All right, now we can do this. So in the next, this next section, we're going to talk about different digital modes. And one of the modes, and I don't have a slide for this, is called Pactor. I forget exactly what the acronym is, but it's a way of sending digital information over HF mostly. This is mostly an HF mode. And because it's an HF mode, and because all modes on HF, except on the 10 meter band, of course, they're restricted to less than 2.8 kilohertz, which is the bandwidth of a single sideband phone signal. Pactor takes up 2.3 kilohertz. So question, what is the approximate bandwidth of a Pactor 3 signal at maximum data rate? Answer, 2300 hertz. And that's of course equal to 2300 hertz. I'm going to skip a question. Question, what is the relationship between transmitted symbol rate and bandwidth? Answer, higher symbol rates require higher bandwidth. And that's why this last question says at maximum data rate. You know, if you're sending Pactor at less than the maximum data rate, and I don't know what that is off the top of my head, your signal will be less than 2.3 kilohertz wide. But this question, what is the relationship between transmitted symbol rate and bandwidth, is higher symbol rates require higher bandwidth. So you know, think about that a little bit. In a signal, let's take FT8. You know, it consists of 8 separate tones, 6, 7, 8. And they have to be far enough apart so that at the receiving end, these tones can all be decipherable, right? They all have to be distinguishable. And so if you pack them too close together, you might not be able to, really distinguish which one is which one at the receiving end. So that's why they get spaced far apart. And that's the key there. The higher the bandwidth, the higher the symbol rate. And it's with symbol rate equal to baud rate, right? I mean, that's the old sort of the old term we use is baud rate. That's why on HF, aside from 10 meters again, the maximum baud rate you can have is 300 baud. Because anything more would start taking up too much bandwidth. I think the maximum data rate on 2 meters is like 1200 baud. And then 440, I don't know. At some point, it as you go up, you get to use more and more bandwidth. So that in the Wi-Fi, where we have Wi-Fi, right? It's like 2.4 gigahertz or 5 gigahertz. Well, part of the 2.4 gigahertz Wi-Fi band, or the 2.4 gigahertz Wi-Fi frequencies, are actually in an amateur radio band. And at those frequencies, we can use whatever bandwidth these routers allow us to use, and which is pretty good rate. So as you go up in frequency, the bands get wider, and therefore we can use higher symbol rates. Question, why is it important to know the duty cycle of the mode you are using when transmitting? Answer, some modes have high duty cycles, which could exceed the transmitter's average power rating. So let's think about that. What's going on here? So if you're transmitting a voice signal, this is actually transmitted power. It's going up and down and up and down. So the average power, is maybe like right here. So even if you say you have 100 watts, that's peak envelope power, the average power, will be down around, 25 to 30 watts. And for a CW signal, you're just on and off. So even though it's 100 watts, the average power is going to be 50%. Because the duty cycle, the time it's on versus the time it's off, is about 50%. And that's how transceivers are rated, right? Again, I'll go use the example of the IC7300. It says it's a 100-watt transceiver, but it's not 100 watts at 100% duty cycle. Because most of these modes, sideband and CW aren't 100% modes. So what is a 100% mode? Well, radio teletype is a 100% mode because the transmitter's always on, and it's always at whatever you set the output power to. So you want to make sure that if you're going to operate teletype or PSK31, which is the same thing, it's always on PSK31 when you're transmitting, that you set it to the appropriate setting. That's the whole idea behind duty cycles. So some modes have higher duty cycles, which could exceed the transmitter's average power rating. If it says 100 watts, that means average power rating. And lots of things are like that too. Like even balance and like other antenna things. They're not rated for necessarily for 100% duty cycle. So you got to be careful. You got to watch that. This is our old friend, the bandpass filter. There's a question here about and this question was on the tech license too, right? Question: why is it a good match? Why is it good to match receiver bandwidth to the bandwidth of the operating mode? Answer: it results in the best signal to noise ratio. So in the case of sideband, you want this to be like 2,500 hertz. And any noise that might be out here, you won't hear it on the output. So you're improving the signal to noise ratio. You're filtering out the noise and you're allowing in the signal, so that gives you a higher signal to noise ratio. So if this was a CW signal, and your bandwidth was 2,500 hertz, well, that's not going to be optimal because your CW signal is only here. So if you had some noise in here, then that noise would still get through. So if you reduce the bandwidth to say 500 hertz, now you've filtered out that noise and you've improved your signal to noise ratio again. So setting the bandwidth to the mode you're operating will help you receive better. Again, I hate to use the word the old days, but in the old days, especially like when I was a kid, I couldn't afford a fancy radio. You you had to make do with whatever you had. And so sometimes the bandwidth of some of these receivers would be pretty wide. So you were receiving multiple signals and multiple noise sources all simultaneously. So you had to develop an ear for the signal, like especially for in Morse code, for the signal you were trying to listen to, and then use your head to filter out the other frequencies. And you actually could get pretty good at that, but it was still better to have a good filter. And you know, with all these new radios, it's like a dream. I mean, like again, the IC 7300, it has you know, digital signal processing, and just, you know, by a few button clicks, you can set, you know, this bandwidth to whatever's the most appropriate. And they work great. These things work so amazingly well. Any questions about that?
Dan, I have a question on power, and
Yeah.
you were talking about PSK 31.
Yeah.
So how do you stay within your average power? I mean, you just watch it and you only transmit and receive, you know, over a shorter period of time?
Well, no. You set the output power to a lower value. And I forget what the rule of thumb is for PSK 31. It's something like 20 watts or 30 watts. You know, if you set the output power low enough, then, you know, that's okay. Now, FT8, oddly enough, is not 100% duty cycle. So you could run 100 watts on FT8 because it's sending separate tones and it's turning the tones on and off. So it has a lower duty cycle than a PSK 31 signal or a teletype signal.
Okay, thanks.
So now we're going to go back to some digital stuff here. That's why I say I'm sorry about the jumping around here. But you know, we talked about PSK 31. And so PSK 31, it transmits, the data rate is about 31 baud, which is real slow, right? But that, in effect, that's about how fast you can type, right? Is at about 31 baud. And the nice thing about PSK 31 is it has a 31 hertz bandwidth, about a 31 hertz bandwidth. So what you give up in speed, again, it's the speed and you know, data rate versus bandwidth. What you give up in data rate, you get in bandwidth. You know, it's very narrow bandwidth. One of the ways it can get by with this is that it uses a type of code called varicode. In varicode, the number of bits varies depending on the character, right? So I should have made a separate thing here. So ASCII, you know, it uses 8 bits per character no matter what. And Unicode is even like 16 bits, right? Something like that. So the number of bits will vary depending on the code you're using. And PSK 31 uses varicode, which is a variable number of bits. So E, which is the most common, and they decided on the codes by looking at the frequency at which these letters appear in the English language. So E is the most common. It's got a 2-bit code. O, 3 bits. A and I, 4 bits. And you know, the others are similar. You know, it can go up to like, I think 8 or 9 bits. these are the capitals. Capitals are used very infrequently, right? And when you're transmitting PSK31, you want to use uh, uh, uppercase letters as least often as possible. So a capital E is 7 bits. A capital O is 8 bits. Capital A is 7 bits. Capital I is 7 bits.
What about the control characters? How many bits are those?
Oh God, I don't know. That's a good question. Yeah, you can look it up. You know, just Google varicode and see what it is. I don't know that. I don't know that in varicode you have control characters though, because if it's for PSK31, there's no need to send a control character.
What about backspace?
About what?
Backspace.
I'm sorry, I didn't understand it.
Backspace.
Backspace.
Oh, backspace. I don't know. Good question. I should have had I should have printed off the whole code. But you can backspace actually in PSK31, I think. So let's compare this to Baudot code. Baudot code is the code we use in RTTY, in radio teletype. And this is an old code. I mean, you know, they had teletype back in the 30s and 40s, I think. It's a 5-bit code. All the characters are 5 bits. Well, let's think about that. So 5 bits gives you 32 combinations. Well, you got 26 alpha characters. So how do you do capitals? Well, they're all capitals. How do you do numbers and punctuation? Well, there's actually one of these 32 is called the shift character. And you actually shift between 2 character sets. It's kind of a crazy thing. Why we stick with Baudot even for RTTY sort of beyond me. I guess the fact that it's pretty slow. I think this is like 45 baud. At least amateur teletype. So you want to send as few bits as possible. So, question, what does the number 31 represent in PSK31? Answer, the approximate transmitted symbol rate. Question, which type of code is used for sending characters in a PSK31 signal? Answer, varicode. Question, which of the following statements is true about PSK31? Answer, uppercase letters use longer varicode bit sequences and thus slow down transmission. So, you know, use as few capitals as possible. Question, which of the following describes Baudot code? Answer, a 5-bit code with additional start and stop bits. Question, how are the 2 separate frequencies of a frequency shift keyed FSK signal identified? Answer, mark and space. So teletype, we don't necessarily say zeros and ones, we say mark and space. Again, that's sort of a holdover, you know, a legacy thing. But a mark could be a 0 or it could be a 1, depending on how you set things up. So they're called mark and space, and they could be either 0 or 1. I think mostly we use mark for 1s and spaces for 0s, but I've never been a big teletype operator. Any questions about the codes? All right. We talked a little bit before about the WSJT suite. one of the modes in there is a thing called whisper. It's a weak signal propagation reporting. And it uses a similar kind of technique to send very low power signals and send and receive very low power signals. And there's people that set up a station to be continually receiving whisper signals, and they report whatever they're receiving back to a website somewhere, and this website then plots all the transmission paths it's getting the data on. That's kind of amusing, and you can look at this because it's weak signals. You can look at this website, and if there's a transmission path between near your house to some other place, you can bet at 100 watts you probably have a good shot at making a contact in that area. So this thing is called Whisper, and again, it's part of the WSJT suite. So question, which digital mode is used as a low power beacon for assessing HF propagation? Answer, Whisper, WSPR. So a lot of the digital modes like PACTOR and WinLink and APRS, that's another one. They all use packet. They transmit data in packets. And if you remember, we used this figure in the tech class. This is a sort of a thematic representation of a data packet. APRS, packet radio, PACTOR, etc. Question, what part of a packet radio frame contains the routing and handling information? Answer, the header. So there's a flag that says this the start of the packet. The header contains routing information. This is the actual data, followed by a check to ensure that you receive the data correctly, and then a flag to say the packet's ended. Like I said, PACTOR, we also use packets, but in PSK 31, when we're sending PSK 31, we're not sending packets, just sending data. And there's no error correction at all in a PSK 31 transmission. So if you don't receive all the phase changes correctly, you're going to get some garbage on your screen. Well, in PACTOR, you're actually trying to send good data. You really do care about the data integrity. So when a station receives a PACTOR packet, it does perform a check, and if the check doesn't match the data, then it sends what's called a NAC, a NAK, not acknowledged, signal back to the sender, and the sender will resend the packet. So question, in the PACTOR protocol, what is meant by a NAC response to a transmitted packet? Answer, the receiver is requesting that the packet be retransmitted. And that's, again, just to make sure that all the data is sent and received correctly. Question, what action results from a failure to exchange information due to excessive transmission attempts when using PACTOR or WinMore? Answer, the connection is dropped. So if you've got two stations, and remember this is HF, HF conditions change, it's very dynamic. And if the transmission path goes away, well, what happens? You just drop the connection, say, sorry, can't transfer any data. And, it's actually a similar thing happens with your internet connection, right? I mean, we're sending packets back and forth over the internet here. If I unplug the Ethernet cable from my computer, well, all of a sudden I don't have a connection, and the router says, well, okay, that's it. I'm not gonna try and talk to that computer anymore. Another way to do that protocol for handling this is called automatic repeat request, or ARQ. So question, how does the receiving station respond to an ARQ data mode packet containing errors? Answer, request the packet be retransmitted. So it's a little different than the Pactor protocol, but all these data modes have their own protocols, and that's just another way of handling it. Some of these digital modes have what's called forward error correction, though. So as part of the payload, you might send some extra data bits that allow you to repair some of the data errors that may occur in the rest of the payload. It's called forward error correction. If the check matches, then there's no problem. They don't make use of these extra bits. But if the checks don't match, they try and use these extra bits to figure out which bits are in error and then correct them. FreeDV, which is a digital voice mode that you can use on HF, is one of the modes that uses it. FT8 also uses it. That's one thing that makes FT8 so good. Question, how does forward error correction, FEC, allow the receiver to correct errors in received data packets? Answer, by transmitting redundant information with the data. So this extra data will help you correct errors if some errors occur, but at the expense of sending extra bits, which slows down the overall data rate. So that's the way it is in any technical thing, right? You never get something for nothing. And in digital communications, it's either error correction or data rate. That's one of the trade-offs. I talked a little bit about FLDigi before. FLDigi is one of the programs that you can use for digital data. Oops. Oh, come on. Oh, I hate when I do this. Shoot. I don't know how to get this back in the center.
I think it's under the window menu in the top.
Oh, not that one. Yeah, not that either.
You can still see it. It's all right.
I don't know. No, I didn't want to do that either. Oh, well. So one of the, oh, actually, I have to move it because, oh, let me close this and open it up again. Sorry about this. Um, one of the features of FLDigi is that it has what's called a waterfall display. Oh, come on. Oh, sorry. This is not the right waterfall display. Sorry about that. This is the waterfall display. This is actually a waterfall display from my Flex 6400. Again, this is one of the cool things about new radios. What you see on this waterfall display is a portion of the band and all the signals in the portion you're looking at. Okay, so I'm in this case, I'm looking from about 7.056 megahertz to 7.076 megahertz. And these are all the signals in that 20 kilohertz bandwidth. So here's some CW signals. And you can tell by just looking at them what they are, which is kind of a cool thing. So these are CW signals, once you get some experience with them anyway. And these here are FT8 signals. And if I expanded this, which I probably should have done, maybe I'll do that for the next class. If I expand this, you could probably see actually all the individual 8 tones in there. They have to be pretty big, but we could still do it. And what this is showing you on the top is sort of the real-time signal. So it's the amplitude of the signal being received. And this is a time recording of that. And the higher the amplitude here, the redder the signal is. So, this is a fairly strong signal, and it's a nice red, red trace here. And all these vary a lot. So like this signal here, you can tell that it was strong and then sort of faded out here because it went from red to yellow and narrower too. And this is even narrower. So this is called the waterfall display. Where am I here? Question, which of the following describes a waterfall display? Answer, frequency is horizontal, signal strength is intensity, time is vertical. So that's what this is here, the waterfall display. And like I say, sometimes you can see characteristics of a signal, like if somebody had a very broad signal, and I've done this several times. I mean, you can take a screenshot and then send it to the guy and say, hey, look, I think you got something wrong with your transmitter. And one time I was going to do this, and I said, oh, I don't know. Sometimes when you do this, guys don't take kindly to it. So I'm kind of hesitant. But at one time, this guy actually asked me. He says, how does my signal look? And I had to tell him. I said, yeah, it does look a little misshapen. And so I sent him a screenshot as well as an audio recording of the signal. I haven't heard back from him yet, but at least he asked, and that was good. But there's a question, what is indicated on a waterfall display by one or more vertical lines on either side of a digital signal? Answer, overmodulation. So those are spurious signals that are generated if you overmodulate when sending like a PSK 31 or a teletype signal. You're overmodulating. And I don't have an example. I couldn't find an example of that, but I've seen that when I was operating PSK 31. And the other cool thing about this is, so I'm a big Morse code operator, and I've even gotten to the point where, like, I can look at these signals and see like how long it takes for, like so you see gaps in here, right? And so this guy here, and this is about this gap here. I didn't capture the axes, but this gap here is about 5 seconds. So based on this, I can almost guess that this guy, because it's the same signal on both sides, or at least it looks pretty similar. And I've done this in the past. I'm going to guess that this guy was sending CQ. So I've gotten fairly good at this. So I can like look at the signals and not even hear it, and guess that they're calling CQ. And when that happens, all I have to do is click on the signal, double click on the signal. It changes. Then this is a feature of my radio, not of every waterfall display, but it'll change the frequency to that frequency of that signal. And then I can hear him and then call him if he's calling CQ. So using a waterfall display like this is like a whole new way of operating. Instead of just hearing the signals, you're seeing the signals. You're seeing the band. Once you get used to operating this way, you don't want to go back. You really don't, because it's almost like you're operating blind. Any questions about this? One more question.
So Dan, and that one signal there that's about, Dan.
What frequency?
So it's like 7.063 maybe.
Okay.
There's a strong signal there, but there's no amplitude.
Yeah, he probably just quit sending. If you notice right up by below the numbers there's a little space. That's probably because he probably quit sending. Or when I captured the screen, it's when, this is a Morse code signal, he just wasn't sending anything. So I wasn't receiving anything.
Got it. Okay.
So in this example, how much time has passed between the top and the bottom?
It's about 15 seconds. I've got it set for about 15 seconds.
Great.
But you can set it for, that's like, so the IC7300, I used to have an IC7300. I had it for about 2 years. And then I got a good deal on this Flex 6400. So I sold the 7300, got to 6400. And I like to compare the two. Well, this display is right off a computer monitor, right? So the 6400, you need a computer to operate. You don't need a computer with a 7300 because it's all self-contained. You actually have this little display like this right on the front panel of an IC7300. But because it's in the radio and the radio is controlling that, it's not as flexible as if it was on a computer. So like on this, I can set the axes to whatever I want. I can set the bandwidth that's shown here to whatever I want. And it's very easy to change. To change the bandwidth on a 7300, well, for one thing, you have fixed bandwidths. On a 6400, I can set it almost in infinite ranges. And to do that here, all I do is click on the frequency axis there and drag left or right. If I drag left, it crunches it in. If I drag right, it expands it. It's really wonderful. I don't have to go through menus to change the bandwidth. Where was I going with this? And the same with the time. I can just drag that middle axis up or down and see more time and less amplitude, or see less time and more amplitude. This is about the right setup, for the kind of operating I do. But yeah, this is really really something. This is really a good step forward. So we got one more question here, and I talked about this before. On some of the Wi-Fi signals, the frequencies that Wi-Fi uses. Wi-Fi is an unlicensed service, and amateur radio is a licensed service, and they plop down some of those Wi-Fi frequencies inside what is an amateur radio band, and we're the primary users on that band, and it's in the 2.4 gigahertz band. So, question: on what band do amateurs share channels with the unlicensed Wi-Fi service? Answer: 2.4 gigahertz. And the amusing thing about this is, if there is a interference problem between somebody's Wi-Fi and your 2.4 gigahertz transmissions, you're the one that has the rights here. So like say you lived on the next block from me, and for whatever reason we wanted to set up a high power 2.4 gigahertz link between your station and my station, and that just happens to wipe out everybody's Wi-Fi in the neighborhood. Well, it's their tough luck, because we're the licensed operators. They're just freeloaders. Of course, you probably didn't want to do that, but there is a case, a documented case, where some business was trying to run their factory on Wi-Fi somehow, or set up a Wi-Fi network in their factory, and they were getting this weird interference every once in a while, and they found out it was an amateur station causing the interference. But since the amateurs were the licensed service, it was the business that had to figure out how to get around that. And basically what they had to do is go around and reprogram all their Wi-Fi to use channels outside the amateur radio band, because some of the Wi-Fi frequencies are outside the band. So that's kind of an amusing thing. And with that, that's the end of the material for this week. Any questions? All right.
What are we covering next week?
Let me see. Whatever the next chapter is. Antennas and feed lines. That's always a fun thing to cover.
That's on Thursday, correct?
On Thursday. And I'll try and send out the email tomorrow. I'll upload this video to YouTube tomorrow morning, and then send out the email.
Thanks, Stan. Great session.
I hope you're all enjoying this, and if you, like I say, if you got any questions, please feel free to email and ask.
Thank you, Dan. And in advance, I'm going to be from a new location next Thursday, so it's a much slower connection. I don't know if it's going to work, but I'll be there if it does.
Just turn your video off. If you have just the audio, chances are it'll be fine.
Oh, wonderful. Thanks. Good tip.
Yeah.
Well, thank you and good night.
Good night.